I want to talk about DNA near its melting point. DNA, of course, needs no introduction, so I will not give any introduction to DNA. What is special of DNA that we will use in this talk is that it's two polymers, two strands of DNA. They interact. Of course, interacting systems are interesting, but the interaction is extremely special in the sense that 2 points of DNA, those are the two base pairs, they interact and form a bond only when they have the same length along the two polymers. And therefore, the interaction is that this base pair doesn't, of course, it can form a bond with another base pair producing a loop, but that's biologically a disaster, that's biologically something that should not happen, and there are ways to take care of that, that never happens. Therefore, to understand DNA, what we need to understand is this role of this interaction, which is always at the same length of the polymer. So this special interaction makes DNA special not only in biology, it also becomes a very special material. There is no other material in the world, or one can create a material that will have such an interaction. So as a material, from a material point of view, from a physics point of view, interacting system point of view, DNA is extremely special. And that I want to just focus on two properties of DNA, which are consequences of this, particular special type of interactions. Interacting polymers are different types of objects. There are many types of interacting polymers, but DNA stands out as a very special class. So ever since the structure of DNA was proposed, within a few years, biologically it was understood that this huge number of hydrogen bonds in DNA needs to be broken. And that can be broken by temperature, that can be broken by change in the solvent quality, pH, and there are many other ways of doing that. And this phenomenon is called melting of temperature. You isolate a DNA, put it in appropriate solvent and change the temperature. And what one sees that this double-stranded DNA molecule just dissociates and it gets into two single-strand molecules. It happens at a very particular temperature. That's called the melting point of DNA. This melting point is not like a solid liquid melting point, but we will still call it melting point of DNA. Melting point of DNA depends on the base sequence. It's around 70 to 80 degrees centigrade. It could be as low as 40 degrees centigrade, but the real value is not of importance for us. And it's now a 60-year-old history. There are many studies, there are many theories. Theoretically, DNA melting is controversial. It's understood, but the experimental situation is bleak. So even after 60 years, even we do not know what's the order of this transition. Even though theoretically we can say it can be first order, it can be second order, it can be third order, it could be infinite order. So what we want to do is that this melting DNA near its melting point, we want to do some perturbation. And we will consider two types of perturbations. One is a small perturbation, that's that we will. So we will put a small force on the DNA, and that will act as a small perturbation, and we will show here that it's something very special, very unique to DNA, something happens. Of course, we know now it's a long history ever since this, it was shown that there is an unzipping transition of DNA which came from Bhubaneswar, but that's very well understood. But what we want to show here, bring out some other aspect of this unzipping transition that tells us why this is something very special about DNA. And so it will be more from a thermodynamic point of view. Instead of looking at a microscopic model, we will try to look at it from a thermodynamics point of view without worrying about much of the details of interactions. And then we will consider a large perturbation where we will put a third strand of DNA near a double-stranded DNA at its melting point. And the question, of course, is that two already creating havoc, so why we want to add a third one? That's not just a crazy thing to do, because triple helical DNA was discovered within a few years of this double helix, prediction of double helical structure. And what was observed there is that this Watson-Crick double helical DNA allows a third strand to bind by a different base pairing. That's called Hoogsteen base pairing, and that forms a triple helix. And what is peculiar here is that in a double helical structure, the base sequences are hidden from outside, And so to get the best sequence in biological system, one has to open that, break the hydrogen bond and get the bases out. But the third strand can recognize this base sequence without any need of opening up or breaking of hydrogen bond. It's a very sequence specific recognition without unzipping of DNA. That's that now, though after again 60 years, it has picked up quite a bit, especially in medical literature, because now one can stop a particular gene from working by identifying that sequence by using a third strand of DNA. So triple helical DNA are now very important even in medical field. And DNA is not the only example. DNA, RNA, peptide nucleic acid, where the backbone is a peptide, but there are bases instead of residues. There are bases which would form this nucleic acid. So it also forms triple helical DNA. So there are many examples of triple helical DNA. And during biological processes, there are things that's called strand exchange, that you take a double helical DNA, these red strands, these green ones are the hydrogen bonds, and if there is a region where the hydrogen bonds have been broken, a third strand, it could be a part of this this long DNA molecule, or some other independent strand of DNA can come and form hydrogen bonds with one of these this open strands. So this is called strand exchange, and this phenomena is observed in biological situation in many cases. So this is also something important that happens during dynamics in biology. So with these two, let's go back to unzipping transition. We want to do a thermodynamic approach. Thermodynamics is very general, and to be predictive, we need to make an hypothesis, and that hypothesis actually brings out what's special about DNA. The hypothesis we want to make, it's of course a bold hypothesis, is that the double-stranded DNA does not allow a small unzipping force to penetrate. What we mean by that is that we take a double-stranded molecule and you pull a force. One can do this experiment by using any of these atomic force microscopes or tweezers and so on. So we pull it by a force G, and we expect in all our physics studies, we expect that a small perturbation will give me a small effect, small cause gives a small effect, that there is a proportionality constant, that's the elastic constant, susceptibility and so on. And the claim here is that there is no linear response. The susceptibility or the response function is strictly zero. It's not small, it's strictly zero for small g. Only response is at a large G. If you want to compare that with conventional polymer, that if I take a free strand of DNA, we say above its melting point and pull it by the same force G, we will see a linear relation, again a linear response there, that the end-to-end separation will be proportional to force with a proportionality constant chi, which is the extensibility. So this is our hypothesis, and with that hypothesis, we would like to get the phase diagram, unzipping phase diagram, and compare it with known phase diagrams, known in the sense of from other studies, theoretical studies of phase transition. So there are of course two possibilities. If we look at this, the conjugate variables here is this separation x. The conjugate variables is this end-to-end separation x and the force g. These are the two thermodynamically conjugate variables. So there are two possibilities, that if we look at the isotherm, there could be a first order transition, this is x versus g, and this is the unzipping transition, that there is no response up to this force gc, and beyond gc it's just two free strands, and that therefore would respond like free polymers. Or there is a possibility of second order phase transition. Let's stick to first order transition because it's simpler and easy to explain in the talk. So first order transition, so what we assume is that there is a first order transition at temperature dependent force Gc at T. T is of course less than the melting point, so that the system is bound to start with. And the standard continuity of free energy is expected when we are at this transition point. And then our hypothesis tells us that if I have this force G, then the free energy of this double-stranded molecule at force G should be equal to the free energy of the force of the double-stranded DNA at zero force at that particular temperature, and G is of course less than Gc. And then if we assume linear response or free change on the unbound side, this is the relation I have already shown, this U represents unbound, then the work done, it's a thermodynamic work done, one can just do a simple minded integration, that the work done will be half chi times g square, and one can use these three in little bit of standard thermodynamic argument to compute the free energy. One can write down the expression for free energy of the zipped state. Z represents zipped state or the bound state, and U represents the unzipped state. So one can express using these three statements. The zipped free energy can be expressed in terms of the unzipped free energy plus this extra piece of work done, which is half chi times g square minus gc square. And once we know the free energy, the derivative will give us, again it's a thermodynamic course, take a derivative of that, that will give us the entropy difference. This entropy difference is important because that tells us the latent heat of transition. This is related to gc and gct, the derivative of gct, and this part is now giving us the phase diagram of the unzipping transition. So close to melting, we will, as I said, it's a small perturbation. So this is the transition temperature Tc, and close to that we will use a small force G. So GCT, so this G has to go to 0 because at melting point it automatically opens up. So it will open up even at 0 force. So GCT goes to 0 at Tc, and we assume that there is a power law type. It's not required, we can assume something else, but let's stick to, again for simplicity, we stick to a power law type behavior. If kappa is greater than 1, it has a shape like that. Kappa equal to 1 is more or less a straight line near there, and if kappa is half, there will be a parabolic dependence of the phase diagram. This is our hypothesis. From our hypothesis, we derive this entropy difference at the phase boundary, which is related to Gc times del Gc del T. And if we assume this form, we can immediately find out that delta S should depend on temperature as T minus Tc to the power 2 kappa minus 1, provided the force is small. Now you see, if kappa is greater than half, then this delta S goes to 0 as T goes to Tc, and therefore there is no latent heat. Melting has to be continuous. We can read it from right to left that if the melting is continuous, delta S will be 0, and therefore kappa has to be greater than half. If kappa is exactly equal to half, that's why I showed this picture, then this tells us that Gc is square root of T minus Tc, and that's where we will have a latent heat because delta is now no longer 0. And melting is first order. Again, if we go from right to left, if melting transition is first order, then the phase diagram must have this parabolic dependence close to Tc. Now latent heat has to be a finite quantity, therefore this object has to be finite, and therefore this kappa has to be greater than or equal to half. And what we get is a strict lower bound, that there is no way we can have anything less than kappa equal to half. And what you see here is that there is no microscopic model. Only thing we require is this assumption that the force does not penetrate this double-stranded DNA. And this does not happen in other molecules, it happens only in DNA. So let's compare with certain exact solutions. There are now exact solutions, many models are now known for which the unzipping transition can be seen. So here are just a few examples of the such exactly solvable models. These are based on statistical mechanics models where we start with microscopic Hamiltonian, calculate the partition functions and free energy in the thermodynamic limit and so on. And what was done, I think it was done much before this thermodynamic argument, and with that I have picked just two classes of models. We will call it Y, and this is called B. B represents that we allow bubbles to form, that hydrogen bonds can break locally to create bubbles in DNA, and the other one is that hydrogen bonds can break in such a way that it's like a zipper, that it doesn't allow bubble formation. And the point here is that exact solution shows us that for this Y-type model, there will be a first order melting point, and for this B-type model that allows bubbles, there will be a continuous transition, melting will be continuous. And what we see here is this, as we predicted from thermodynamics, that there is a linear dependence here. It's linear dependence in this particular case, but it's generally, there could be non-linear dependence also, but it's greater than half. And if the melting is first order, there is a parabolic shape of this phase diagram. In fact, there are models where this kappa can go to infinity because of exponential dependence, but those can also be considered by modifying the worked on formula a little bit. So what it shows us that, in fact, you remember that our formula has this term del Gc del T. So this may allow a del Gc del T to be equal to 0, which means that the phase diagram may have a point of maximum here, and that's the point of maximum, and that represents that there is a possibility of re-entrance. This is a re-entrance because, as you see, I come from, as I cool the temperature. But this can be done again in a standard experiment, that you pull it with a certain force G here, and you start pulling it from the unbound side. It will get into the bound state, and then still at a lower temperature, it will again go into the unbound state. This is not thermodynamically impossible. There is no violation of any thermodynamics laws, and this is allowed in our formulation for DNA. Question is there any experiment? So anybody thinking of any new experiment can think of this, because this experiment cannot be done by buying equipments off the shelf. One has to do something different. One needs to change temperature. Can you change temperature in any force measurement equipment? So let's now go to the second perturbation. We will call it a thermal Efimov effect. This is again very peculiar DNA. So giving you a picture of melting, that, as I said, melting happens in this way, that I have this double-stranded molecule with these hydrogen bonds, and because of thermal fluctuation in some region, hydrogen bonds will be broken, and this I will call a bubble. A bubble, in this bubble, the simplest picture would be that it consists of two free polymers starting from one point and ending again meeting at another point, because this distance is much smaller compared to the overall size of the bubble. And the bubble will be characterized by two scales. One will be the number of base pairs broken, number of base pairs broken, that I will call Xi parallel. It's parallel because it's parallel to the backbone of DNA. And the other one is the size it occupies in space. So these two are again the standard quantities in polymer physics, that these two will be related by the polymer size exponent, that the size of this polymer is related to its length to the power nu. If we assume that there are no other interactions except this hydrogen bond interaction, then there are no hydrogen bonds here. So it would be like Gaussian polymer, random walk, and therefore this relation between Xi parallel and Xi would be like Xi square. But in general, it would be Xi going like Xi parallel to the power nu, and nu will be half. If you just compare it, nu is equal to half. And as we approach the melting point, T approaches Tc, the size of this bubble starts growing, and therefore Xi goes to infinity, Xi parallel goes to infinity, because all the hydrogen bonds are broken. So the phase transition can be, or the melting transition can be understood by studying this behavior of Xi and Xi parallel as a function of temperature. What is peculiar here is that there is a scale invariance. I started with this hydrogen bonded DNA molecule of certain bond lengths and so on, but close to the melting point, there is a scale invariance that if I change my scale R by any factor B, the free energy comes out to be B to the power minus 2 times F, free energy per base pair, and this B can be arbitrary. This is called a continuous scale invariance because B is arbitrary. I can choose any arbitrary number. What that means is that I can coarse grain a DNA. I don't really have to look at base pair level. I can coarse grain and start with a coarse grain model, and such things are characteristic of an unstable renormalization group fixed points. I will not get into the details of that. But what we now want to do is to take this double-stranded DNA near its melting point. So in 3 dimensions. So what we will do is that, again to explain things easily, what we will say is that I will take a pair which are more or less stiff. So they are stiff chains, and I keep them. So one is particularly stiff, other one is flexible. Because it's close to Tc, there are these big bubbles. And let's say I call it Z in this direction. So it's a DNA of length n with this big bubble. This is a hydrogen bond. There are a few hydrogen bonds and bubbles of, there will be of course be no unique size of bubble. There will be a fluctuation in the size and shape of these bubbles. Next what we do is add a third strand. It's also a stiff one, but maintain a distance, because it's stiff, we can maintain a distance r between these two strands of DNA 1 and 3. 2 is flexible, and because 2 is flexible, 2 can make hydrogen bonds with 3 somewhere here and there. And what we want to do is that I start with this double-stranded DNA 1 and 2 close to its TC. I now add a third strand of DNA kept at a distance of r. What is the change of free energy? There has to be a change of free energy because of this effect here, which in biology is called a strand exchange. So we will not do a heavy-handed computation. We will do a scaling argument that the effective interaction between 1 and 3 mediated by this flexible 2 can be written in this form, that the change in free energy per unit length or per base pair dimensionally is something energy will come here. The scale of energy close to TC is kBTC, and with that thermal energy, the number of base pairs broken is xi parallel, and therefore delta F by N should be like delta kBTC by xi parallel, and that's actually what we need to understand melting. This is called hyperscaling, and if we use this and forget about that term, if there is no third strand, then that is enough to give us all the features of melting transition of this double-stranded molecule. But now we want an R dependence. This delta F should depend on R. R has the dimension of length. This is already dimensionally correct, and therefore what we must have is a function of a dimensionless argument. And the only way we can make R dimensionless is to divide it by a scale which is the size of the bubble, because there is no other scale available, assuming that only one scale matters. And therefore the form of this delta F is like that. And remember these two scales appearing in this expression, xi parallel and xi, they are not independent. They are related by this polymer size exponent nu. And if this formula makes sense, then it has to make sense also at t equal to Tc, and at t equal to Tc we know that xi and xi parallel go to infinity, and therefore this expression should be such that xi and xi parallel cancel out as we approach Tc. And one can quickly work that out, that the only way that's possible is that delta F by N goes like -1 by R square. This is something extremely unusual, because this change in free energy is the effective interaction between 1 and 3, and this argument tells us that these two strands of DNA interact because of thermal fluctuation via a long range interaction which goes like 1 over R square. 1 over R square is something we do not study in physics. We avoid 1 over R square. Why we avoid 1 over R square? One can look at the Schrodinger equation, why we do not study 1 over R square in quantum mechanics. We stop at 1 over R. We go to R square potential for a harmonic oscillator, but we avoid this. This is because we write down Schrodinger equation. I have observed all the constants, irrelevant constants in these expressions. So this is our Schrodinger equation in this 1 over R square potential. Now I can do a scale change, that all these x's will be replaced by x prime, which is just b times x. B is a scale factor, going from angstrom to micron or angstrom to kilometer. So b is that scale factor. And if I put that scale factor, you see I will get 1 over b square from this del square here. I get 1 over b square from that 1 over R square. So in terms of this prime variable, I again get back Schrodinger equation with the same potential. It doesn't happen for any other potential. And that b square comes with E. And this is very unusual, because if E is an energy eigenvalue, B square E is also an energy eigenvalue for any value of B. This goes against the basic theme of quantum mechanics, that bound states are discrete. This tells me that if I know one eigenvalue, I can choose any value of B and I will get another bound state of that energy B square E. This is the peculiarity of 1 over R square. That's why we do not study. And what we see is that DNA is an example where we cannot avoid this 1 over R square interaction. So what would be the, coming back to DNA, what will be the, do I have time? Okay. So what the effect of this is, what is the effective potential between the two strands of 1 and 3? So let me again remind you. So we are talking about the effective interaction between 1 and 3. This is mediated by these short scale hydrogen bonds formed by 2. But we are forgetting 2. It's the interaction between 1 and 3. So there are these hydrogen bonds. We are maintaining the distance r. So 1 and 3 cannot form hydrogen bonds. That's the hydrogen bond length scale. Then there is this 1 over r square. And if the distance r is much larger than the bubble size, then of course 2 cannot form a bond with 3. It will form only bonds with 1. So there will be an exponential decay of this interaction. And this crossover from 1 over r square to exponential is somewhere in this regime where separation is order of average size of the bubble. Now, as we approach the melting point, xi goes to infinity, and therefore this whole thing gets pushed to infinity, and therefore beyond this hydrogen bond scale, what we get is 1 over r square. And this 1 over r square, so let me say again that I started with 2 polymers, 2 strands of DNA at its melting point, but they are supposed to be separate. They are supposed to be separate. I put a third strand, I get an attraction between them, and the 3 together will form a bound state. And therefore, because of this 1 over r square at Tc, when it takes over the whole range, it will form a 3-stranded bound state. It's not the conventional triple helix. Triple helix is at a microscopic order at the hydrogen bond scale. This is on a much bigger scale. So single chains are free. They are in a relaxed state. Melting point thermal fluctuation generates this 1 over r square interaction. So they should have been in the free state, but because of this 1 over r square interaction, the 3 chains are now bound where no 2 are bound. So it's a collective bound state. I remove 1 chain from that system, they will fall apart. So it's a state where 3 chains are bound where no 2 are bound. There are examples known which are called Borromean rings. You see, this is something that the 3 are together, and you cut any one, other 2 will fall apart. But that's topological. In our case, there is nothing topological. It's purely entropic, and that's why it's very peculiar to DNA, and we will call it Efimov DNA. We call it Efimov DNA because Efimov showed this problem in the nuclear physics context that 1 particle, 2 particle systems are trivial, all can be solved. Infinite number of particles are also a very common system. We work hard, but we have procedure to study them. But 3 particle problem is extremely difficult. And what Efimov showed is that you take 2 short range, these 3 particles with short range interaction, take square wave potential we solve in the first lecture of quantum mechanics, and choose this potential such that the bound state energy is exactly 0. That has an infinite scattering length. I do not know how many like scattering here. I hated scattering during my quantum mechanics course, but that's all right. But this infinite scattering length is important. Bound state has 0 energy, means the width of the wave function is infinity. And now you put a third particle with the same potential. It's again, so because of the 0 energy bound state, you take any 2, its bound state potential energy will be 0. But these 3 together will give you an infinite number of bound states which are connected by this simple geometric series. And G is called an Efimov constant, and this is called Efimov effect. This Efimov effect is strictly at this particular case of infinite scattering length, but this tells us that this 3 particle will form a bound state which will exist in the region of the potential where 2 particle will not be bound. And that's what we are seeing in DNA. So is this possible? So this argument actually can be verified. We have verified it using lattice renormalization group approach in several papers.